I teach architecture and engineering technology down at COTC in Newark. We're sponsoring the Toothpick Bridge competition. I've been a judge several years at the Newark competition, so I guess I've seen how this works both ways. And I've had some experience in it, so hopefully I can lead you in the right direction, answer some questions, and hopefully we'll get you to have a successful bridge through this project. Okay, let's start in the beginning. Is just kind of a little bit of a lesson on bridges. It was prepared mostly by the Licking County engineers. I kind of stole their presentation. Rory gave it to me and I revised it. Oops, hit the right buttons. Thanks. Okay, civil engineering, the branch of engineering that specializes in the design and construction of structures such as bridges, roads, and dams. This is what civil engineers do in their careers. While doing their work, civil engineers must keep a keen eye on the cost of a project as well as how the project affects the environment, safety, and government regulations. So all that stuff's important. They have to think of multiple parts of their job. And an important part of building a bridge is learning from failure. So you don't want failures to happen, but usually if something does fail, if you think of all phases of our lives, if something fails, we usually study it and try to figure out why it failed. So really critical in bridges that can involve loss of life. So why would we build a bridge? Anybody have ideas why you might build a bridge? I saw this and I thought it was kind of like why the chicken crossed the road, to get to the other side, right? So that's pretty much what a bridge does. You can cross over a natural or man-made obstacle, stream or river. Most of you probably are acquainted with bridges that cross over streams or rivers, I'm guessing. Over highways, I'm guessing you've seen those too. Over a valley, there's a few, I can't think of any right immediately around here, but get down in mountainous areas and they cut across valleys here and there. And over railroads, those are around a bit. So there's all kinds of people involved and careers involved in building a bridge. You have people like the engineers, surveyors, operating engineer, the people that kind of engineer the way it's going to get built. Computer technicians have to help support. There could be plumbers involved with the bridge for plumbing and waste lines and stormwater. Of course, asphalt pavers, electricians if the bridge has lighting. And then carpenters to help build the bridge, build the formwork for concrete, etc. So lots of careers involved in it. Bridge basics. Now this is stuff you're going to want to study up on as you work on your bridge, but I'm going to review those real quick just so you know these terms. And the most important term is span. That's the distance between two bridge supports. So if you were building a bridge from this desk to this desk, span is this opening between them, so the bridge has to arch over that. So if this was 3 feet and you build a 3-foot bridge, what would happen in total length? It's going to fall in the hole, right? So remember, span is that inside opening, so the bridge would arch over it and have to land on the table and on the table. So it's critical for you to understand span, or Rory's going to throw you out of the contest when you get her. Not really, but she's going to punish you. Compression. Compression is just a force. When you push things together, that's a compression force as you try to mash things. Tension's the opposite as you try to pull things apart. Pulling things apart is tension. So your bridge is going to have those two forces in it, compression and tension, and that's kind of the magic of what you're going to do with these toothpicks is engineer them so that toothpicks don't compress and fold up and they don't pull apart. Scour, that's kind of a bridge term. You shouldn't have scour with your bridge. That's a term for the water kind of taking the footings out from under a bridge. So force of water in a stream acting on a bridge. Wind load, that's just the wind. You would be surprised. Think of sailboats. The wind pushes pressure. So the wind has to take those pressures or those loads that push on it. Resonance, it's a vibration in something caused by external force like wind. So resonance is kind of a sway. It kind of relates to music. It's that kind of harmonic movement of something that is resonance. Torsion, that's the twisting force, so things torse. We're going to see some examples of these in a failing bridge here in a bit in my video rigs. So torsion, it's a force that tries to twist your bridge. History of bridge construction. So maybe that was the first bridge, I don't know. Or maybe that could have been just a log across a river. That's where the concept of how to cross a stream might have come from, when these logs fell across a stream and it turned into a bridge. Then the Romans got a little more complex with that. They developed the idea of an arch and started to build these complicated bridges. Does anybody know what this really is? It's not just a roadway. Have you ever seen it and what it does? It's an aqueduct. So there's actually, at the very top of it, it took water into cities. So pretty neat concept of this kind of bridge. The middle deck here was for cars and people. Clear up there, there's a little trough for water that took water into cities. The Romans loved their public water. And this is a pretty famous bridge. This is the Coalbrookdale Bridge over the River Severn in England. First, important in a couple ways, it's the first metal bridge, and they developed the idea of mass-producing parts. So they cast these pieces, brought them out here and assembled a bridge. So kind of mass production and for steel bridge, pretty strong. Steel and concrete bridges evolved from there. So most of our bridges today are made out of steel and concrete. You'll see some old stone arch bridges and things, but for the most part today, steel and concrete are the materials that we build bridges out of. There's about five different kinds of bridges covered quickly in this. So an arch, that's like the aqueduct we saw. An arches want to function all in compression, so it's all compressive force smashing down on the arch, and that holds them together. Then when you have trusses have a combination of tension and compression in them. So different pieces all have different, so if you looked at this lattice work, some of those are in tension, some are in compression. It kind of varies which one's in which. And probably your toothpick bridge is going to mostly work that way, as more or less a truss, with some members in tension, some in compression. Let's see, there's beams, just giant beams. It could be made out of steel and concrete. Generally, the top of the beam is going to be in compression, the bottom in tension. Suspension bridges, steel cables, so all these cables hanging down, and this cable would be what kind of force going in those? Can you guess? Is that stuff pulling on it or pushing on it? You guys are like my class at school. Nobody wants to tell me. So that's tensile force, right? That's like a string when you're pulling it. So it's tension in all those numbers. Let's see, cable stayed are very similar, except the cables go right to, I don't have any diagram, there's some coming up, we'll see those. Cables go right to the bridge deck rather than a master cable. So arch bridges, like we looked at the Roman one, oldest type of bridge. The arches direct loads to piers or abutments. Great natural strength, spans between 200 to 1,000 feet, and they do tend to all be in compression. Arches don't like tension. So that's kind of all these pieces are pushing in on each other, especially right here at the base of the arch. There's an example of one, a stone arch bridge. And there'd be one that's kind of a steel. It's steel or concrete. I guess it's steel. So this is an arch, bottom of it in compression, and then the members bring it down. Beam bridge, they're probably the simplest to build. They're just taking a simple beam. Loads carried through piers to the ground, least expensive, and rarely span more than about 200 feet. So kind of medium span structures. And there's the way it works as a beam. The top of the beam, like the roadway deck, close to that area, it's going to be trying to get pushed together, while the bottom of the bridge will be in tension. So that'd be an example of a beam bridge. Most of the highway bridges you see around here would be a simple beam bridge. And then truss bridges. Now this is closer to what I'm guessing you're going to build for your toothpick bridge. This relates pretty closely to that. So made of a combination of triangles, directs loads from diagonal framework to piers. The piers will be what supports the bridge. You're going to be building those out of your toothpicks too. More rigid than a single beam, used for longer bridges, and combined with other types of bridges. Span length's a little bigger here, 120 to 750 feet. So there'd be an example of a truss type bridge. There's a great example of one down here across the river as I drove into town. Nice big old truss bridge. I think it's for the railroad. Railroad bridges are usually pretty good examples. So think about those as you build your toothpick bridges. So that'd be a good example of a railroad bridge. And see that is a truss type bridge. Some of those members are in tension. If you look, the members that are in tension are rods. The members that get more compression in them are more of a beam type kind of thing. So you can almost see where the tension and compression is in that particular bridge. There's one down in Licking County over the walking path these days, or bike trail. So that would be a truss type bridge, right? And the suspension bridges, I don't think there's many of these around here, right? If you go somewhere where there's big, expensive bridges, they suspend roadways from main cables. The main cables are supported by high towers and supported by anchorages. They're the most expensive, spans from 1,000 to 700 feet. One of the earliest ones was down in Cincinnati. If you've ever seen the Roebling Bridge down there, it's one of the first early suspension bridges, I think about 1860. Good example of one. So that's the way they work. Golden Gate Bridge, you may be familiar with that. It'd be a suspension type bridge. So these piers hold those compressive forces, and then this stuff is mainly hanging it by tensile forces. So not so easy to build with toothpicks, but you can try it.
Are the New York City bridges an example of the suspension bridges?
Brooklyn Bridge would be by the same guy that Roebling did the Cincinnati Bridge, and then the one in New York was the next bridge after that. I think it's always neat that something so local preceded something slightly more famous. Same guy. His next bridge was Brooklyn Bridge. So there's a good example of a suspension bridge. You can see all the cables laced in together, really helping to support. If you look, there's kind of a truss hidden under here. So it's got a truss that the cables are helping out. Cable stayed bridge, slightly different. They look very similar, but they're slightly different in concept. The tower supports the bridge deck directly, so it doesn't have that big main cable drape that comes down with the tension members to the bridge deck. Towers direct the load to the ground, similar to the other one. Spans of 2,500 to 7,500 feet. So there you can see how the cables themselves go straight down, kind of harp-like in the way they go out to the bridge deck. So there'd be an example of one. So not really that main cable slinging and the cables down, but cables harped out directly to the bridge. Pretty neat picture. Learning from failure. Now you're ready to see this. You may have to try some toothpick bridges and fail them to see where you're going to have failure, just like some of these big bridges have failure. The Tacoma Narrows Bridge in Tacoma, Washington is a famous one. We're going to look at it quick at the Silver Bridge. I think I threw this one out. And then Minneapolis I-35, that was in the news. It seemed more recently, but I guess that was 2007. So Tacoma Narrows, famous failing bridge. Let me see if this video works. I don't guarantee it. Maybe something that happened. Let's see. Somebody seen the videos of this? It's kind of
My grandmother had just crossed it.
Oh, really?
Mm-hmm.
Yeah, that would be kind of a dramatic thing. But there's sound. I didn't try that hard.
Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Okay, sound did work. So that would be an example of a suspension bridge, and that would be kind of that harmonic failure, and the swinging kept grabbing the wind and making it go until it reached its failing point. So that, let's see, yeah, this was date of failure November 7th. So was it literally that day, same day?
Yes.
Oh my gosh. Was it swinging when she went across?
No, she passed away so long ago,
Yeah.
I don't really remember, but
Wow.
to remember that story.
I would think that'd be a good family story. So today they can do kind of computer modeling, and there's a lot more sophisticated stuff. They can see how these are going to react in the wind. Silver Bridge, more close, that's down over the Ohio River in Gallipolis, Ohio. It was an I-bar type suspension bridge, so kind of a hybrid between a truss and suspension. Had a material failure in 1967 and fell in the river, I think about now, so I think it was holiday-ish time or something. Oh, it says there, December 15th. So there's some pictures of it falling into the river. It was big drama back in the day. So they learned about redundancy. That's the idea of having not just one thing. If one thing fails, maybe something else will help out and carry the load. And bridge inspections and kind of checking them out. Minneapolis I-35, that's a more recent one. That was just in 2007 in Minneapolis, Minnesota. It was a deck truss, also material failure. I think due to this, there might be some engineering problems or Ross, I forget the exact details. There, that was big in the news. It was a highway. It's a big highway. You can see literally it just kind of collapses into the river. It looks fairly harmless there, but that looks a little scarier. But if you're one of those cars, I think you would have found it much more dramatic of an event. So falling bridges is not good. We have to learn from disaster and not let these things happen. Here's some cool ones that are successful. Here's a new bridge in Columbus, Ohio. And a Bering Straits bridge proposed. This isn't built. This would link Russia and Alaska. Have you been around any of these? Any of them close by? Old-fashioned covered bridges. You might want to look at their structure. They usually have fairly simple internal structure that would be replicatable. That's the right word. Could be copied for a toothpick bridge. This looks like a cable-stayed bridge. Where it is, doesn't matter, Denmark and Sweden. Pretty fancy modern bridge. These would be kind of the combination of art and simple design, right? Since these are beautiful and also kind of artistic and dramatic. Another one, cable-stayed, pretty much. A stretch from the German islands to a Danish island. This one down in Portsmouth, Ohio, there's a cable-stayed bridge. And Licking County Road again, so another truss bridge. And here's a bridge that goes out to a tunnel, so there's some of those on the East Coast, that kind of combination bridge tunnel across water. And there's another cable-stayed.
That last one, they actually are proposing that they build those islands. So those are man-made islands.
Those are man-made islands. Look it up. That's pretty cool. And there's another kind of arch / different things going on there. Almost suspension. How about this one? What kind of bridge is that? How about a bridge for boats? That happens too. So canals crossing another river, might need a boat canal. Some of our old canals around here had some of these crossings. Okay, so now the challenge. You ready to get to what your challenge is? So, how many of you have read the toothpick bridge kind of problem? A couple of you have. That's good. You've done your preliminary work. And hopefully the group that's already building the bridge has read it too, I hope. Okay, so your challenge is to design the most efficient, economical, and aesthetic bridge using only toothpicks. That's standard toothpicks, the kind you pick your teeth with. Not those big hibachi sticks or other stuff, but real toothpicks. The structural efficiency is going to be equal to the weight supported divided by the weight of the bridge, and that's going to give you a ratio of how many times its own weight the bridge carries is essentially what that comes down to. So you want the bridge to be fairly light and efficient and carry lots of weight is the goal. So if you build a really heavy bridge, that means in proportion it's going to have to carry that much more weight to still get a better ratio. The judges are also going to judge the aesthetics of the bridge, whether it's kind of pretty, whether you've done some unique things with it. So try to make your bridge attractive and not just glued together a mess of toothpicks. And then you're also going to give some presentation on cost effectiveness to glue a number of toothpicks that you've used. So now, span. Remember I said that word is really important. Span is important. The bridge must have a minimum clear span, so that's that. If I were building a bridge over these tables, the bridge would, abutment or the pier would sit out there. It has to come across to over here. That's your span, is this open space, the river, the water. You don't want your bridge to end up in the water. If you look here, here's the blue water. So there's the river. The road kind of comes to here. So this must be 12 inches. The bridge is going to have to sit out here. You don't want the feet of the bridge in the water. The water is 12 inches wide. Do not put parts of the bridge in the water. And the other trick, well, I guess we'll see more of that coming up here. So is that all clear? Any questions on span? That's a critical concept. I want to make sure you're all comfortable with the idea of span. All good on that? So then you're going to put a bridge deck on it. The bridge deck interior width must be at least 1.5 inches, and we'll talk more about why. This will be tested with a matchbox car. The deck must be solid so that the car can travel the length of the bridge, and then we're going to have a loading block that's going to go through the deck. So there's going to have to be a hole. I've got more diagrams of this. There's going to be a hole here in the middle, and the loading block that's going to try to break your bridge is going to fit on top of that. Here's your span. Once again, remember, here's the water edge to water edge. The bridge is going to be longer than that, right? Because you got to get your bridge out here so it bears on the land on each side. The water's 12 inches wide. So there's your span. Here's the bridge deck width. So the width of that has to be 1.5 inches. Now the car doesn't have to get back down to the road, right? It's just going to be a flat deck. So don't worry about having ramps up to get the car onto the bridge.
It's going to magically teleport onto your bridge and drive across it.
The forklift is going to put it on the bridge and off on each end or something. So don't worry, you don't have to ramp up to it. Pretend that the bridge ramps are built out there for you. You're going to neglect that part of the problem. But you do need a bridge deck that the car can drive across, except for you're going to have a giant pothole in the middle of the bridge. That's going to be where the wire goes through, the rod goes through. So there's the rod that's going to go through your bridge. This thing is going to have to set down in that bridge deck. So that's why you need width and a flat area at the middle of the bridge, because this rod's going to go through, and then the kind of machine or the weighting device is going to attach to the bottom of that rod. So you need at least 2.5 inches wide in the bridge. So this area has to be 2.5 inches.
1.5 to 2.5. 2.5 is the max.
Oh, 1 point, okay, yeah. So that's that part. It's got to be at least 1.5 to 2.5. Yeah, there's the max. Yeah, that's confusing. Okay. 1.5 inches minimum because the block is that big, but it can be, so you don't want to exceed 2.5 inches on the deck of the bridge. And then the other trick that causes problems for people is you've got to get the bridge up so a boat can go under it. So you're going to build these feet. We're not going to provide the feet. So you've got to build an abutment, build a pier, build something that holds your bridge up 2 inches off of the water. So a little 2-inch boat can float down the river and go under your bridge all the way across this 12-inch span. So all the way through there, a boat has to be able to cross. So So no part of your bridge can be out here in the water. It has to be 2 inches up, so you need a 2-inch by 12-inch area that's clear under your bridge. Does that all make sense? So you're gonna build the height of the bridge. Like I said, if a car drives up to it, don't worry about ramps to get it on. Your car is gonna drive up here. And we'll just pretend that somehow it got up on. The maximum height for the bridge, for any part of it, is 8 inches. So nothing can be over 8 inches tall. It doesn't have to be 8 inches tall. It can be a lot shorter than that. But maximum height for the structure of it is 8 inches. Nothing taller than 8 inches. It doesn't have to be 8 inches. Loading connection, that's a critical component. The bridge must be able to accommodate the loading block, and it's about 1.5 by 2 inches. It's going to need a hole at the midpoint of the deck, so it's going to sit where the car would drive. In the same place the matchbox is going to drive across there. So there has to be a hole in the center of the bridge that will allow that 1/4 inch rod to pass through the vehicle deck. So right in the middle of this orange block, there'd be a 1/4 inch hole that rod can go through. So this rod is going to have to go down through your bridge with a hole in the middle, 1/4 inch. Does that make sense, everybody? And then material specifications, you're only allowed to use round, uncoated toothpicks. You can't use more than 800 toothpicks. And you'll be surprised, you don't need a ton of toothpicks to do a good bridge. Doesn't take a ton, you'll be surprised. The more toothpicks you use, like I said, the heavier the bridge is, the more weight you're going to have to end up carrying. You're only allowed to use good old Elmer's white glue. You can't use epoxy, you can't use wood glue, you can't use hot glue, and you can't paint, and you can't use super glue. So only good old-fashioned Elmer's wood glue. And even though it might be pretty, you can't coat the bridge with any material, paint, or stain, so it's got to be raw toothpicks. Any questions on any of that? So just plain old white Elmer's. Do you give them the glue?
And the toothpicks.
And toothpicks. Well, there you go. So there's no way you can go wrong on that. And these are showing, hopefully, some ways that you can glue the toothpicks. Remember, toothpicks can only be glued in the following ways, and that's end to end, so you can overlap the tips no more than a 1/4 inch. So end to end, touch their little tips, 1/4 inch. So right here, this kind of connection, there can't be more than a 1/4 inch connection here. Up here, same thing. So overlaps no more than a 1/4 inch at all these joints. If you look at that, they're pretty much tip to tip, and you're seeing a little blob of glue there. So tip to tip, blobs of glue. So tip to tip, end to end, 1/4 inch overlap maximum. End to side, so you can glue into the side of another toothpick. So here's a toothpick going across. There's toothpicks coming into the side of that toothpick. Once again, about a 1/4 inch is no more, and these don't really have much overlap at all. If you look at all these connections, they just not much overlap. About a 1/4 inch of overlap. You can glue tip to side. That's another legal way to glue. So tip to tip, tip to side. And no side to side glue. If you look, there's 2 toothpicks here, right? Everybody see 2 toothpicks? 2 toothpicks. Is there side to side glue? The toothpicks glued together this way? No, so you can't put glue in here. You can only have your glue down here at the tips. So if you look, there's a little space in there. You can let your toothpicks touch, but don't make the judges get their magnifying glass out and look for glue. You shouldn't have glue. No bundling, no creating laminated beams, no glue side to side. So this area in here, no glue. Only at those 1/4 inch tips. Glue in the tips, here, here, here. That's the only place you should see the little beads of glue in the connections. And you'll want to go back, you might want to put your bridge together and then come back and kind of re-glue those a time or two and make sure you get a nice glob of glue in those tips. But once again, you can't spread it out beyond a 1/4 inch in those connections. Any questions on that? That's another critical area. No side-to-side glue. Rory's going to be looking for that. She's out to find the side-to-side this year. I'm making her sound nasty, aren't I?
Yes.
She's really very nice. Don't be scared. Unless you do side-to-side gluing. Bridge specifications. So once again, any bridge not meeting these specifications will be penalized, and I forget, in the rules we've set up what your punishment's going to be. Anything physical. So hints, these are some hints. So make absolutely sure you understand that word span. So go home and when you start working on your bridge, do some research on span, find diagrams that properly show span. Make sure you understand the height of the bridge. Remember, do you remember how high the maximum of a bridge can be? There'll be a quiz here in a minute. How high? Very good. You are paying attention. That's great. And your bridge deck, remember you've got to have a solid bridge deck that you can drive that matchbox car across. What are you going to put in the middle? You know? You're going to have that 1/4-inch hole, right? You guys are going to do good. You're going to do very good. Triangulate the structure. If you remember those truss-type bridges that we looked at, triangles. So every direction you look at your bridge, if you don't see triangles, that's setting up for failure. Because a square without a triangle wants to collapse. And the only thing that's going to hold that square up is kind of the moment force or that glue in the joints. So if there's no triangle connecting it together, they tend to want to fold up. A square is not a very stable form. If you look, here's your square. But if you look down through there, multiple places, it triangulates. And there's pieces in there that triangulate the structure. So you want to see triangles. Hold your bridge. A lot of people are real good at, as you look at it from the side, the way it spans the river, great triangles. When you look at it this way, they forget, and the bridge just wants to fold up, even though it's a real good truss. They fold up. And that's what happens if they fold up. It doesn't work. So my class just did their bridges this week, so this is the debris from the successful and unsuccessful bridges. Lots of hours of toothpick gluing in there. So any questions on that? Can I help you with any specific questions?